Hey group, I'm Michael, and we're doing 8.7, number 18, which is asking us to solve this differential equation, y double prime plus 4y prime plus 4y equals 15e to the negative 2x times natural log of x plus 25 cosine x. Now the first thing we should notice is that our forcing function is going to be a pain to integrate when finding our particular solution. But the textbook has a theorem in it that says that we can find two partial particular solutions and add them together to make one particular solution. Now, one part of our particular solution is going to be involving this 15e to the negative 2x times natural log of x. And our other part of our particular solution will be involving this 25 cosine x, because those are way easier to solve individually. Now, what to find? We want to find our complementary solution and our particular solution, which will consist of yp1 and yp2. And our final solution will be our complementary solution plus our two particular solutions that we will find. So first, let's find the solution to the homogeneous case. y2 plus 4y prime, y double prime plus 4y prime plus 4y equals 0. Now this can be rewritten as the operator d squared plus 4d plus 4 operating on y equals 0. And this can simplify to just d plus 2 squared. And this will give us an r value of negative 2 with a multiplicity of 2 because we have this squared right there, which means we'll have a y1 and a y2, and our y1 happens to be e to the negative 2x, and our y2 is equal to xe to the negative 2x. And this will give us a complementary solution of c1 times e to the negative 2x plus c2 x e to the negative 2x. Now we can find our first particular solution using variation of parameter method involving the 15e to the negative 2x times natural log of x part of our forcing function. So first we'll write the particular solution equal to u1 times y1 plus u2 times y2. And our y1 was e to the negative 2x, and our y2 was x e to the negative 2x. So ultimately, we're going to want to solve for u1 and u2. But first, we have to solve for u1 prime and u2 prime using this system of equations, which comes from our constraint, the top equation, which we used to get to this equation, which is equal to our partial forcing function. Now, to solve for u1 prime, we'll use Cramer's rule, and our numerator determinant will be 0x, 15 natural log of x, and 1 minus 2x. And I factored out a e to the negative 2x out of both of these equations, so none of these will have an e to the negative 2x in it. So solving for this determinant, this will equal 0 when we multiply it. And then we'll get a minus x times 15 natural log of x. And our bottom determinant will just go to 0 because we have a 1 times 1 minus 2x. So we get 1 minus 2x for that. Minus a negative 2x, which will give us a plus 2x, which will cancel out this minus 2x and leave us with just 1. So our u1 prime is negative 15x natural log of x. So our u2 prime is just this determinant, and we will have the same determinant for the denominator, so I'll just put that as 1. And 1 times 15 is 15, minus 0 times 1 is 0, so we just get 15 for our u2 prime. Now we can solve for u1 and u2. So our u1 is equal to the integral of negative 15x natural log of x times, or dx. And we factor out a negative 15. And so now we have the integral of x, natural log of x dx. And to solve that, we will use integration by parts. And our u will be our natural log of x. Our dv will be x dx. And this will give us a du equals to 1 over x dx. And our v will equal x squared over 2. And so now, replacing our integral with this, we get x squared over 2 times natural log of x minus the integral of x over 2, because we get x squared over 2 times 1 over x. Solving this integral, we just get an x squared over 4. And then I factored out a x squared over 2, but you can just leave it like this if you wanted. So I had got this for my u1. Now for the hard part, solving for u2. So our u2 is equal to the integral of 15 dx. And for that, I got 15x, but you might want to double check on your own. Plugging these in for our particular solution from above, we have our u2 right here, our u1 right here, our y1 right here, and this was our u2, this was our y2, and I just multiplied the x's together. So that's our first particular solution. Now on to the second one, using annihilators, and this one's involving our 25 cosine x part of our forcing function. So we have y double prime plus 4y prime plus 4y equals 25 cosine x. Now from above, we know that this simplifies to d plus 2 squared operating on y equal to 25 cosine x. But we want a annihilator that will make this cosine of x go to 0. And looking at this awesome chart, we get that d, if you plug everything in, we get d squared plus 1 operated on cosine of x. We'll make that go to 0. But we got to put it on this side too. And since we already found our r values from the complementary solution for this operator, that means we can just focus on this one. And this one will give us an r value of plus or minus I. And this is a case 2 of an r equaling a constant plus an I times a constant, but right now it's just a 0 plus or minus just I. And multiplicity of 1, because it's the one exponent right there. This will give us a second particular solution in the form of a naught cosine x plus a1 sine of x. Now, we don't want an a naught and a1 in our particular solution. We need to solve for those. So we're going to want to take the derivative and second derivative of this particular solution, plug it back in to this equation, and solve for a naught and a1. So for y p2 prime, I got minus a naught sine of x plus a1 cosine x, and y p2 double prime equals negative a naught cosine x minus a1 sine x. So I rewrote this down here, and so it's easier to see how everything plugs in. So we get this as our y double prime, this is our y prime, this is our y. And when you distribute and combine like terms, you get 3a naught times cosine x plus 4a1 cosine x minus 4a naught sine x plus 3a1 sine x equals 25 cosine x. Now notice that we have a cosine x over here. In fact, we have 25 of them, which means when we add our cosine x terms, it should come out to 25 cosine x. Or in other words, 3a naught plus 4a1 should equal 25. And since we have no sign of x's over here, that means our negative 4a naught plus 3a1 should equal 0. Now we have a system of equations we can solve. So just from this bottom equation, we can get that a1 equals 4/3 a naught. And plugging that into our top equation, we get 3a naught plus 4 times 4/3 a naught equals 25. Combine and distribute and whatnot, we get 25/3 a naught equals 25. A naught equals 3. And plugging that back in to this, we get a1 equals 4, which means our second particular solution is yp2 equals 3 cosine x plus 4 sine x. Now we can put it all together. So I rewrote our complementary solution and our first particular solution in case you forgot what they were. And so our solution will be in this form. And now we just plug everything in. So our yc, our complementary solution is just c1 e to the negative 2x plus c2x e to the negative 2x plus our first particular solution, which was negative 15 over 2x squared times natural log of x minus a half times e to the negative 2x plus 15x squared e to the negative 2x plus our second particular solution, which was 3 cosine x plus 4 sine x. And that is our final solution to this particular differential equation. Thanks for listening to all that. I'm sure it was definitely not all convoluted and was definitely easy to follow. And hope you have a great rest of your day.